Let's take a look at the theory that led to the preparation of the dive profiles used up to now. In 1908, a scholar named John Scott Haldane arrived at the conclusion that the human body could subject itself to a maximum low pressure equal to half of the absolute pressure to which it had previously subjected, without visible consequences. His goal was to find a mathematical method for calculating safe dive profiles, and his reasoning was as follows. Subjecting a gas to an instantaneous compression, it begins to dissolve in the liquid because it encounters a certain gradient. But as time passes, the liquid absorbs gas and tissue tension increases, thus reducing the gradient. Consequently, the speed of absorption also decreases. In mathematical terms, the absorption curve is exponential. In particular, it was noticed that the tissue tension over a certain time interval increases by a value equal to half of the gradient. After another equal interval, it will be half of the new gradient, and so on, up to 6 intervals. At this point, tissue tension draws close to 100%. On a molecular level, during each time interval, half of the molecules involved in the exchange pass into solution. The same principle holds true for the opposite direction, in which the gas abandons its state in solution to return to its free state. The value of that determined interval of time is called half-time, and it varies for every gas-liquid combination. Thus, a mechanical law was created that described the behavior of tissues during the gas absorption and release phases. But the human body is not formed by a single homogeneous tissue. Therefore, it was schematized as if it were formed of 5 families of tissues, each with tissue half-times of 5, 10, 20, and 40, and 75 minutes. Today, these families are called compartments. These compartments are mathematical contrivances for performing calculations. In the model, 2 axioms were considered. First, the exchanges take place independently for each compartment. They are considered to be in parallel. Second, no interaction is considered between one compartment and another. It was thus possible to calculate the tissue tension of each compartment during the descent and ascent phases, calculating the elimination of excess gas. Taking the maximum halving limit as valid, certain decompression stops were established when the tissue tension in a compartment was double that of the ambient pressure, thus allowing the compartment to eliminate a little of its excess gas, enough to allow the diver to ascend a few meters after the stop. Later, the United States Navy performed some calculations and contributed some variations. Some compartments were modified, and above all, the maximum 2-to-1 relationship was no longer used for all the compartments. They began to consider only the nitrogen in the air as an inert gas, and each compartment was assigned a different oversaturation ratio. Thus, the famous decompression stops were created, which were calculated at 40, 30, 20, and 10 feet deep, corresponding to 12, 9, 6, and 3 meters. These calculations were also extended to repetitive dives, giving rise to the dive tables still used today.